Hey there, and welcome. If you look around, I mean really look around, you'll see that everything is moving, from planets zipping around the sun to the very blood in your veins. But how do scientists talk about all this motion with any kind of precision? Well, today we're going to dive into the fundamental language they use to describe a world in constant motion. Let's get into it. All right, here's the game plan. We're going to start with the big question. What even is kinematics? From there, we'll build up our understanding with some core ideas like position and displacement. Then we'll introduce some really important ways to classify things, and we'll wrap it all up by looking at the powerful tools that let us actually predict motion. Okay, so first things first. When we use this word kinematics, what are we actually talking about? I mean, just think about it for a second. A car heading down the highway, a quarterback throwing a perfect spiral, a satellite orbiting Earth. To understand any of that, let alone predict it, we need a common language. We need a set of rules, a mathematical way to describe what's happening. And that, right there, is kinematics. You can think of it as the geometry of motion. It's all about the how. How fast is something going? How far did it travel? Which direction is it headed? But, and this is the important part, it completely ignores the why. We're not talking about forces or what's pushing or pulling on anything, not yet. For now, we're just observers, learning how to describe what we see.
So to describe any kind of motion, you've got to start somewhere. Literally, you have to be able to say where something is in the first place.
The absolute starting point for all of this is an object's position. But, just saying the car is right here is kind of useless, right? Here, relative to what? And that simple question is where things start to get really interesting. Have you ever had this happen to you? You're just sitting on a train, looking out the window at the one next to you. Suddenly, you see it start to move backward, and for that split second, your brain is convinced that you're moving forward. It's this weird little illusion, but it perfectly highlights a huge point. All motion is relative. It depends on who's doing the looking.
And that brings us to this idea of a frame of reference. It's basically the viewpoint we choose to measure from. We have to pick a starting point, a zero, and decide which way is positive. Whether you're standing on the station platform or sitting inside that train, you're in a completely different frame of reference, and how you describe the motion is going to be different.
Now, let's build on that with our next idea. We're going to look at two terms that can really trip people up at first, but trust me, the difference is super clear once you see it. Okay, so distance is the total ground you covered. Think of it like the step counter on your watch. It just adds up every single step. Displacement, on the other hand, is way simpler. It's just the straight line change from where you started to where you ended up. It doesn't care about the wiggly path you took to get there. So, let's imagine this. You walk 4 kilometers south, then you make a right turn and walk 3 kilometers east. If we want to know the total distance you traveled, that's easy. You just add it up. 4 plus 3, that's 7 kilometers. But what about your displacement? Well, that's the shortest straight line path from your starting point to your finish line. You can see how that makes a little right-angled triangle. And if you work it out, that shortest path is just 5 kilometers. See the difference? You walked a total of 7 kilometers, but you're only 5 kilometers away from where you started. The difference between distance and displacement is the perfect way to understand our next two big ideas, which are absolutely essential in physics, scalars and vectors. The difference here is actually incredibly simple, but it's super powerful. A scalar is just a number. It has a size or a magnitude. Think 20 degrees Celsius or the 7 kilometers we just walked. A vector, though, has that number, but it also has a direction. So not just 5 kilometers, but 5 kilometers southeast. Not just 90 kilometers per hour, but 90 kilometers per hour east. That little bit of extra information, it changes everything. So looking at our table, we can see distance is a scalar. It's just a number. But displacement, that's a vector. It's got both a magnitude, that 5 kilometers, and a direction, southeast. And you can see how a bunch of other things we measure fall into one of these two camps. See how speed and velocity are paired up, just like distance and displacement? Let's check those out next. Okay, so we figured out how to describe where something is and how far it's moved. Now we need to talk about how fast all of this is happening. And this is exactly like our distance and displacement story. Speed is the scalar. That's the number on your car speedometer. It only tells you how fast. Velocity, on the other hand, is the vector. It's your speed and the direction you're going. This means you can actually have a constant speed while your velocity is changing all over the place, like if you're driving in a circle.
And following that logic, acceleration is just the rate of change of, you guessed it, velocity. Now here is the key thing to get. Acceleration is not just speeding up. Because velocity includes direction, you are accelerating if you speed up, if you slow down, or if you change direction. So yeah, hitting the gas, slamming on the brakes, or just turning the steering wheel. Believe it or not, those are all forms of acceleration.
All right, time for a classic physics brain teaser. This one seems like a total contradiction at first. Just think about it for a sec. Is it possible for something to be perfectly still, even for just an instant, while it's accelerating? The answer is a big yes, and here's the perfect example. Picture throwing a ball straight up in the air. It travels up, it slows down, and for one tiny split second at the very tippy top of its flight, it stops. At that one instant, its velocity is 0. But is it accelerating? You bet it is. Gravity is pulling down on it the entire time, which means its velocity is constantly changing, even at the exact moment it isn't moving at all. So, we've basically just built up an entire vocabulary for talking about motion. Let's pull all of our new tools together and see what we've got. These right here, these are your building blocks: position, displacement, velocity, acceleration, and understanding the difference between a scalar and a vector. If you get these concepts, you have the key to accurately describing how pretty much anything moves, from a simple falling apple to a galaxy billions of light years away. And once you have the words, you can start making sentences. And that's what these are, the kinematic equations. Now, don't worry about memorizing these right now. Just look at how they connect everything we've talked about. That S is displacement, U and V are velocities, A is acceleration, and T is time. What's so cool about them is that if you know just a few of those values, you can plug them into these formulas and solve for the ones you don't know. They let you predict the future, which is pretty amazing. So we've spent all this time learning the language to describe motion, but we've very deliberately dodged one giant question, haven't we? What actually starts the motion? What stops it? What makes it change direction? What are the pushes and pulls at play? Well, that is a question for the next step in physics. That's a question for dynamics.